Welcome to Apps 1, Waveguides, number 10, building waveguides. Wow, we come a long way from number 1.
Yep.
So in this presentation, we just have some parameters that most of us know, and we haven't really done many calculations with them. Phase velocity, group velocity, and impedance.
Well, we last mentioned these all the way back.
Yeah, so omega now, we're doing phase velocity down the guide. 1d, again, omega over kz. We know what that is. We derived it, do some scaling, and we see that the phase velocity is the intrinsic velocity of the material times this factor.
Yep.
Notice anything fishy about this?
So this is going to be less than 1,
Uh-oh.
which means after you do the multiplication, the phase velocity will be greater than the material velocity. And let's say the material is air.
Yeah.
So air, so you have 1 over mu naught epsilon naught.
Yep. Square root of it.
So that's speed
So
of
we-
light. You're saying that the phase velocity can be greater than the speed of light?
The math is okay. So is this violating Einstein's relationship?
Is it?
What is a phase velocity measure?
Ah, okay. So this phase of velocity is just the speed if you track one point on a wave in the waveguide in this case, but it doesn't necessarily carry information.
Yeah, no energy is carried by a point. You need a blob of points. And to get a blob, we need the group velocity.
Yes.
And we know how to calculate that. That's the formula. And if you do it for this simple case, and that proof is left to the reader, we can show that the product of the two is indeed the material velocity squared. So we don't violate Einstein's relation, and the group velocity compensates with the inverse of this factor if you do the derivatives, and the product equals v squared.
Okay, good. So Einstein's still right.
Einstein is fine. Finally, we want to mention that the waveguide has an impedance just like transmission lines, and here it's computed as the ratio of EX to HY, or minus EY over HX.
So is this the effective impedance going down the guide?
For the wave.
For the wave, okay.
And it's transverse. It's in the XY plane. We're taking ratio of X to Y.
So this this effective impedance actually changes depending on the mode you're traveling in.
Right, because we know that K perpendicular depends on M and N. So the impedance depends on the mode. We're doing TE with HZ. Of course, there's TM with EZ. And also, we can see that the group velocity, same thing here, because we have K perpendicular appearing. So these are all mode dependent. So now the next thing is, we've got all these modes. We'd like to know what the fields look like. And we're going to do it for a simple case when M is equal to 1 and N is equal to 0 for TE.
Isn't this a tough one?
It's not too bad, but we'll only do it intuitively, not analytically, so you get a feel for it.
Okay.
So let's go on. For 11, we're going to do apps 2, which are the shapes of the field lines for simple cases.
The ride just keeps getting longer.
The ride is longer. We're almost at the end of it for this particular section.